Welcome to QSTI Prep Academy. Today, we're breaking down EPA Method 3. Look, this is the absolute bedrock of stat gas analysis. If you're planning on stepping foot out in the field and doing this correctly, you've got to know this standard inside and out. So get your notebooks ready, focus up, and let's get to work. You're here because you want to pass your qualified source testing individual exam, right? Well, mastering Method 3 is absolutely non-negotiable for that certification. We're going to strip away the fluff today and look directly at exactly what you need to understand to succeed on the test and, more importantly, out there on the stack. Here's our roadmap for this explainer. 1. Welcome to Method 3. 2. Safety and equipment setup. 3. Field sampling procedures. 4. Analysis and leak checks. And 5. Calculating dry molecular weight. So first things first, what's our actual objective? Method 3 is used for one primary reason. We have to find the dry molecular weight of a sample from an effluent gas stream. And how do we actually get there? Well, by extracting a gas sample and analyzing it specifically for the concentrations of carbon dioxide and oxygen. Without those two percentages, you literally cannot calculate the molecular weight. It's really that simple. All right, moving into our first major area, safety and equipment setup. Out in the field, you've got to understand exactly what we want versus what's trying to get in our way. Our target analytes here are O2 and CO2, but you will definitely encounter interferences. For example, acid gases like sulfur dioxide, they can totally mess with your CO2 measurements. And for O2, you've got to watch out for unsaturated hydrocarbons like acetone, nitrous oxide, and especially ammonia. Listen, ammonia is a huge trap because it chemically reacts with the oxygen-absorbing solution itself. If ammonia is present in your effluent gas stream, it has to be removed before you run your analysis. No exceptions. Quick safety check here. ORSAT and Pyrite analyzers don't run on magic. They run on highly corrosive chemical reagents. We're talking about heavy hitters like potassium hydroxide, sodium hydroxide, cuprous chloride, zinc chloride, and hydrochloric acid. You absolutely do not want these on your skin or in your eyes. So follow the manufacturer's operating instructions to the letter and strictly observe all those warning labels. Do not cut corners with these chemicals. Now, when you're setting up a single-point grab sampling train, don't overlook the small details. Right at the very front, you've got a filter, typically just a plug of glass wool tucked inside either stainless steel or borosilicate glass tubing, and that's there to remove particulate matter. Then, the gas is transported to the analyzer using a simple one-way squeeze bulb. It's a pretty basic setup, but every single connection has to be perfectly tight. Now compare that to the integrated gas sampling train, which we use for a sustained sampling method. Right after the probe, you're going to see an air-cooled or water-cooled condenser. This piece is absolutely critical because it pulls out excess moisture that would otherwise completely mess with your pump and your rate meter. From there, a leak-free diaphragm pump pushes the sample into a flexible bag, usually made of materials like Tedlar, Mylar, or aluminized Mylar. Okay, let's transition over to field sampling procedures. If you're out there doing multi-point integrated sampling, I need you to lock these numbers into your memory right now. The minimum traverse points depend entirely on your duct's size and shape. For circular stacks less than 0.61 meters, that's 24 inches in diameter, you need a minimum of 8 points. If it's a rectangular stack under that same equivalent diameter, it's 9 points. For literally everything else, it's a 12-point minimum. Trust me, they love to test you on these exact thresholds. When you are actually running that integrated sample, there are some very strict operational rules. You absolutely must sample at a constant rate, keeping it within plus or minus 10%. Also, the sampling run needs to be simultaneous with and for the exact same length of time as the pollutant emission rate test. And here's your ticking clock. Once that sample is taken, you have exactly 8 hours to analyze it for CO2 and O2. Not tomorrow morning, within 8 hours, period. Let's take a quick breather here. Are you absorbing all these field rules? Because out on the stack, you definitely don't get an open book. If you're finding this explainer valuable, please hit subscribe. And listen directly to me. If you want to pass the QSTI exam, send an email to qstiprepacademy@gmail.com, and right there, we've got the resources to get you fully certified.
All right, let's get back into it. Next section, analysis and leak checks.
Now, the method officially allows for either an ORSAT or a Pyrite-type combustion gas analyzer to measure your O2 and CO2 concentrations. But here is an incredibly useful quality control pro tip. If you're primarily using an ORSAT analyzer, you can actually take periodic fire readings in the field to verify and confirm your ORSAT results. It's just a really great way to ensure your primary analyzer hasn't drifted off the mark. Moving an ORSAT analyzer around frequently causes it to spring leaks, so running a thorough leak check on site is highly recommended. So here's the exact procedure you need to know. Step 1. Bring the liquid level in each pipette right up to the reference mark on the capillary tubing. Step 2. Close the pipette stopcock. Step 3. Raise the leveling bulb to bring the confining liquid meniscus onto the graduated portion of the burette and record its position. And finally, Step 4. You just observe both the meniscus and the pipette liquid level for exactly 4 minutes. So how do you actually know if it passed? Well, 2 strict conditions have to be met over that 4-minute window. First, the liquid level in each pipette must not fall below the bottom of the capillary tubing. Second, and highlight this, it's a highly testable number, the meniscus in the burette must not change by more than 0.2 milliliters. If it shifts by more than 0.2 milliliters, you fail. You'll literally have to disassemble everything, clean it, re-grease the stopcocks, replace the rubber connections, and run the entire check all over again. All right, homestretch, let's talk about calculating dry molecular weight. Before we hit the main equation, we've got a preliminary step. We already know our percentages of CO2 and O2 from our ORSAT or fire analysis, right? Well, to determine the remaining percentage of the gas, which is made up of nitrogen and carbon monoxide, you simply add your CO2 and O2 percentages together and subtract that sum from 100%. It's just basic subtraction, but it sets up everything else we're about to do. And here is the big one, equation 3.1. To find MD, or the dry molecular weight, you multiply 0.440 by your percent CO2. Then add 0.320 multiplied by your percent O2. Finally, add 0.280 multiplied by your combined percent of N2 and CO. You really need to commit this formula to memory. But look, you shouldn't just blindly memorize these multipliers. You really need to know where they come from. They're actually just the molecular weights of the individual gases divided by 100. Carbon dioxide's molecular weight is roughly 44, so divided by 100, we use 0.440 as our multiplier. Oxygen is roughly 32, hence 0.320, and nitrogen and carbon monoxide both sit right around 28, giving us that 0.280 multiplier. Once you understand the logic behind it, the formula becomes almost impossible to forget. But of course, there's a catch. It's what I like to call the argon anomaly. See, equation 3.1 completely ignores the presence of argon in the effluent gas, but ambient air actually contains about 0.9% argon, which has a molecular weight of 39.9. By ignoring it, we're basically introducing a negative error of approximately 0.4% right into our calculation. Now, as a tester, you can choose to include argon in your analysis, but be warned, doing so requires specific direct approval from the administrator. So, we've covered the entire procedure today, from setting up your grab train to respecting those highly corrosive reagents, verifying your 8-hour windows, passing that strict 4-minute leak check, all the way to finally calculating your dry molecular weight. My final question to you is this. Are you prepared to step out onto a real stack and apply Method 3 flawlessly, without letting a hidden interference like ammonia completely ruin your O2 readings? Study these slides, know the standards inside and out, and I'll see you out in the field.